Well, I have the great pleasure. I'm sorry that my voice is not perfect because of the weather. I will do my best. I have a great pleasure to introduce Professor Tobin. Professor Tobin is a complete chemist. If you look to his career, he's been able to cover a large number of problems of the modern chemistry. In a very master, is really a master of chemical science. Professor Tobin is now professor at the University of Northwestern University, but in order to see how much he's able to cover different areas of chemical science, he is now Vladimir Ipatev Professor of Catalytic Chemistry, Professor of Material Science and Engineering, Professor of Applied Physics, Professor of Chemical and Biochemical Engineering. So just to let you know what many different fields of chemical science are covered by this unique scientist. I know him since we were both postdoctoral, and we were both involved in the development of organometallic chemistry. And he started as a synthetic organometallic chemist. But then he moved, like many of us, to catalysis, to polymerization, when he developed the new catalyst, one-side catalyst for polymerization, after the latter catalyst, were the most modern catalyst. And also, he did a great contribution to the understanding of the polymerization process, and of making also one metal catalyst, one central catalyst by interaction of metals with surfaces. But what is really impressive, after a lot of work on carcinostatic metal complexes and synthetic CFX metalloproteins active sites, is that very recent work, the last 20-25 years, in the area of molecular optoelectronics and molecular microelectronics, nonlinear optics. And what is astonishing, how he's able to produce new molecules, new organic or new organometallic color, which produce this kind of physical properties which are then applied for microcircuits and for the modern synthetic macroelectronics. I think that in this particular area is actually considered really the top in the world, and in many respects is really a master of this new area which is growing very fast. And this is an area perfectly chemical as origin and perfectly physical as application. And this is something unique which is now happening to the chemical science, to be an intercrossing very strong between ability to make new molecules, ability to predict properties, and ability to cover areas which are originally not chemicals. And this is the great, strong appeal of Professor Tobin. I don't cite all the honors, awards, etc. that he made, but what I think is very important that he's a real scientist, he's a pure scientist, but he's also able to apply his ideas, and he's also, which is defined by the enormous number of patents he has, which has been able to apply. And this is something typical of what I call a modern chemist. A modern chemist is not only a pure scientist, must be a pure scientist, must also able to use the chemistry for the power, which is that particular science. And I think this is the strong appeal of Professor Tobin, which I would say is now, I consider, a unique example of a modern chemist.
Thank you, Professor Marx.
Well, this keeps falling down. Let me begin by saying how honored I am, deeply honored, to be elected to this esteemed academy and to join the ranks of my 2018 classmates who have spoken already. And what I wanted to talk about today, I'm used to teaching in front of a classroom at 8 in the morning. And so I learned to walk back and forth, because if the heads are no longer following me, I know they're asleep. But you look awake, so let's not worry about that. I wanted to talk about a topic in catalysis, and you might wonder, why should I care about catalysis? After all, when we were in high school, we all learned that the function of a catalyst is to reduce the activation energy of a chemical reaction to make it go faster. But what I would argue is there's much more fascinating science than just that. For example, how it traverses the pathway rather than the extreme activation energy one is very, very intricate. There's a huge amount of science here. I've drawn it as a two-dimensional plot. For lots of enzymes, it's no doubt a three-dimensional plot. But if we could understand this, and the way we understand this, the impact is enormous. And by catalyst, I mean there are three different kinds. There's a beautiful article by Gabor Samarjai arguing that we should think of all of these as one science and look at their similarities rather than their differences. But homogeneous catalysts are solution phase, biological, and by that I mean largely enzymes, are solution-like phases, let's talk about it that way, and heterogeneous catalysts are surface catalysts. And why should I care? Well, catalysts and catalytic processes account for about 30% of the world GDP. And the consequences for human health and well-being are absolutely enormous. For example, the Haber process to make ammonia for nitrogen, if all the Haber plants today were to stop, within a year, approximately 2 billion people would starve to death. So malnutrition is a very important factor in any sort of human health. The catalytic converter, if you looked at pictures of Los Angeles in the 1970s with air you couldn't breathe compared to today, this technology was really the main factor. And if you think of how many cases of lung cancer, emphysema, et cetera, that it prevented, that's reality. And modern pharmaceuticals, almost all of them, whether they're abiotic or biological, ultimately how they're produced goes back to catalytic processes. The importance in modern science you can also understand, in terms of recognition for doing catalytic chemistry. And these are some selected examples, but you can see these for asymmetric catalysis for pharma materials. These again for new kinds of materials and also for pharma. These again going back to heterogeneous catalysis, fundamental understanding of processes on surfaces. And these also are for pharma and all sorts of chemical manufacture where you have to connect molecules and connect atoms in very selective and very efficient, atom-efficient ways, among other reasons to minimize pollution by doing this kind of chemistry. One example that I thought I would follow up on a little more, which is a classic example of the impact of a catalytic chemistry, is this reaction here and this scientist here. It also impinges on some of the issues that I think every scientist has to deal with. So this reaction, it was thought at the end of the 19th century, was really impossible to master. There would seem to be no way to produce ammonia for fertilizer, and so that's what it's used today on a huge scale. And what Haber discovered was a catalytic way to affect this reaction. You see, thermodynamically, it's not necessarily so difficult. It's the inertness, the strength of the nitrogen-nitrogen bond. And he and colleagues, first at the Kaiser Wilhelm Institute, commercialized this process on a huge industrial scale. And when World War I began, the British and the French assumed Germany would have no source of the nitrates needed for munitions because the British Navy would blockade their ports. And in fact, this reaction totally changed the whole picture. And so the opening of the Battle of Verdun, the German bombardment was firing 200,000 projectiles per hour into the French lines. So this made a huge difference. And this Haber process mechanistically is still not well understood today. But as I said, in terms of fertilizer, it feeds about 1/3 of the world's population today. About 60 to 70% of the nitrogen in our bodies is Haber nitrogen. So it's essential to human life. On the other hand, you could make munitions from this ammonia, and that was part of the complexity of what was done with this process. Well, Haber went one step further, and he had the idea, after seeing the carnage, that maybe the war could be shortened by, I know it sounds terrible, using poison gas. And so he actually went into the trenches himself to do the first, I hate to use the word experiment, and with disastrous success. He came home and told his wife about this success, and that evening she committed suicide in their garden. She was also a chemist. So he received the Nobel Prize, ultimately was forced in 1933 to leave Germany, and he died on his way to what was then Palestine to join what is now the Weizmann Institute. So this enormous complexity of what science means when you have this giant catalytic process. Now, in his Nobel address, he raises one fascinating question, and it's a biological one. In his Nobel address, he says, if someone could understand how this enzyme, nitrogenase, works, which fixes nitrogen and turns it to ammonia at room temperature, atmospheric pressure, under air, he said, no one will need my process any longer. And this is the enzyme. It's an absolutely fascinating puzzle in mechanistic chemistry. It requires the transfer of 8 electrons and 8 protons. Reducing the dinitrogen molecule is still a challenge today to do in a chemical process in the laboratory. But this structure, this magnificent enzyme, does it beautifully. And this is the actual chemical reaction. So it's very complex, takes a lot of reducing power to reduce N2 to ammonia. And the holy grail, since when Haber's Nobel lecture was in 1920, was to genetically engineer nitrogenase so that plants could produce their own fertilizer. And sadly to say, even today, we're really unable to do this, but it remains a holy grail. And this is a metalloenzyme. It's a catalyst, a catalytic entity. So now, let me turn to another catalytic reaction that I thought I would take as an example from my lab to talk about today, and this is olefin polymerization. So these are very, very simple, ridiculously simple molecules, and you might wonder what useful could you ever do with them? This with the shale gas revolution in the United States, these are extremely cheap and extremely abundant. More about that in a minute. The two scientists who devised a catalyst that could turn these into useful materials was Giulio Natta at Milan and Karl Ziegler at Mulheim. And they designed a catalyst. And the catalyst they designed is a heterogeneous catalyst. It's not really completely understood today, as ironic as that might seem. But by looking at solution models for this, which turned into solution realities, there's a very intricate set of of mechanisms by which the metal center activates the olefin. It inserts into a growing chain to form a polymer attached to the metal center. This is called propagation. There's a process by which the chain growth terminates to produce a polymer. And what do I mean by a polymer? I mean a plastic, the kind of plastic that surrounds our world. And we'll say more about these polyolefins in just a minute. And then a new chain grows. So you say, well, probably, that's a low probability event. How's it really going to happen? How can it become practical? We'll say in a minute. But each of these catalytic centers, if it's working successfully, will produce 1 million or so chains within a minute in an industrial process. So let's say a little bit more about understanding what's going on and what are these polyolefins really like. So, for example, we all know polyethylene, polypropylene. I'm looking for a piece of plastic here, but I'm not going to knock on this. Enormous production, that very simple catalytic chemistry I showed you. This is the U.S. production, and in 2015 it was about 400 billion pounds of plastic. And what's remarkable about them is their versatility. If we want to make automobiles more fuel efficient, we need to make them out of low weight materials that don't require foundries and iron and steel. All sorts of medical applications in modern hospitals. The amount of things that are made of polyolefins are staggering. Solar cells, protecting them, all sorts of agriculture, from irrigation to all sorts of ways of treating the plants to make the agriculture more efficient, to be able to feed more people. And what's particularly remarkable, let's talk about molecules. This is an example of this little complex with a cyclopentadiene ring and other groups. You might wonder, what could I make with ethylene that would be very different? And with the right catalyst, or let's say catalyst 1, you could make a kind of molecule that is an extremely effective lubricant. Less friction in driving our world and our economy means less energy consumed. Another one, with these branches, there's a huge amount of physics in how these chains entangle, whether they're strong, whether they fall apart. And the branching is a very important part of that. Hyperbranch, we have something that's just coming out it's just in press in Nature Catalysis. These are very, very good lubricants. They're better than any other hydrocarbon lubricant anyone's found. This is a process that nobody ever thought could happen, that you could make a polymer this simple with these simple building blocks that has hard blocks and soft blocks for everything from soles of athletic shoes to things like that, to make our life more comfortable and to make them with energy efficient and minimal polluting byproducts. So our motivation is to discover new catalytic principles and intertwine that catalytic chemistry with macromolecular science, meaning physics, chemistry, materials properties. Now, I have to interject one FYI, which some people raise, and the question is, okay, you've got these polymers, these plastics that you make from gas that comes out of the ground, but wouldn't it be better to use nature's biology to make plastics rather than instead plastics which are biodegradable? And I'm not, I'm not preaching, but this is a very convincing study where on this is a whole variety of polymers, and the red ones are bioderivative polymers, and these ones I just told you about are the polyolefins, and this is life cycle impact of producing them, and this is adherence to green design principles. And what you find, the drawback of most of the bioderived ones is you need a large amount of land area to grow these plants that you're going to harvest to make polymers from. You're going to need a lot of water and fertilizer and tractors, and that may be land area that's needed to fill feed the 9 billion people on this earth that we're facing. The other thing is, if something is biodegradable and you're producing it and degrading it in such large scale, we better ask very seriously what the degradation products are and whether those are going to harm us. So when you factor in all of these properties, you conclude that the really bad part about the polyolefins is they're too chemically inert. You can't throw them in the ocean. You can't, just dump them off the side of the road and hope they'll degrade someday. So the answer is very simple, which, if you think about it, makes a lot of sense. All of these kinds of materials ought to be recycled. Okay, so now let me talk about some of the science that my group did. To test the ideas of Ziegler and Nada, or to improve on them, we needed some way of making a co-catalyst. This is an organometallic molecule to react with the pre-catalyst to make the kinds of structures we had seen on surfaces and which surely are important in a lot of the Ziegler and Nada catalytic chemistry. And this is all done in solution. But we didn't want a catalyst which was a black box. We wanted a catalyst we could isolate, characterized by X-ray diffraction, calorimetry, spectroscopy in situ, and this is the result. This is one example. This is the molecule here. The olefin inserts, some molecules are better behaved than others. Come on, now it doesn't want to turn. Well, we'll turn. Okay, we'll do this one then. So in each of these cases, this is the fluoroborane that's abstracted a methyl cation. This makes a methyl anion. This makes a metal cation, which some people initially refused to believe we had been able to make, because it's a 14-electron B0 cation. Don't ask me why it's doing this, but in any case, you got an idea. So you can put these in a bottle. You can do calorimetry, X-ray diffraction, everything you need to understand what this catalyst is made of. And then ab initio calculation showed this is purely an electrostatic interaction. Really important for chemistry. It's hard to stretch two-electron, two-center bonds. Remember the Morse curve. But electrostatic systems are very, very flexible, and we can see by computation the olefin inserts and grows a chain. Alessandro Motta, one of our Italian collaborators from the University of Rome in the audience, has been very important in this. So this particular catalytic system, we partnered with Dow Chemical, and to date they've made about 30 billion kilograms of polymer, of plastic, very high grade, very strong, very flexible, very tailorable, using our catalytic chemistry. This is about $100 billion worth of sales. So where can you go beyond that? And let's see what nature can teach us. Nature still makes the best catalysts. I surely believe this. And nature uses lots of catalysts that don't have a single metal center, but have two metal centers operating cooperatively to achieve a function that no one single metal by itself could do. And here's an example of a urease enzyme. There are phosphatase enzymes. There are lots of others. And what happens is one nickel in this di-nickel catalyst activates water, makes it a stronger nucleophile. That means to attack this urea, and very rapid and very selective hydrolysis of the urea to ammonia and CO2. So can we design polymerization catalysts that function the same way? And here's a very simple kind of structure. One titanium, one zirconium. The zirconium makes short chains. That's part of its chemistry. The titanium makes huge, long chains. And you put them in the same molecule, and each time the zirconium makes a short chain, you can't even detect this. It's captured by the titanium and makes some very unusual kinds of polymers. This R group then in the short chain becomes a long branch on the backbone of the polymer. Really interesting rheological properties, processing properties. But you can push this further, and this is where I want to show you how far you can push it. I'm going to take a catalytic center which makes polymers, single site, And then I want to take a catalytic center that operates by a completely different mechanism to turn ethylene into 1-hexene. It only brings 3 ethylenes together. What would happen if I made a catalyst where these were connected, where I can vary the length of this tether? And one of the reasons I want to do this practically is 1-hexene is very expensive to make for the polyolefin industry. I'm going to have this little molecule make polymer and make 1-hexene around a single molecular locus. Okay, this is just to give you an idea of how far one can push this and how much you can learn. There's a cycle that makes the 1-hexene. There's another cycle that makes the polymer. And the key thing is when the 2 molecules, the titanium and chromium, are joined and in close proximity, almost every 1-hexene molecule that's made by this cycle is captured by the titanium. When I explain it to this is American universities, when I explain this to the trustees of Northwestern University, I say, think of it as a football game. So the center throws the ball to the quarterback, hikes it. He then, or she, tosses it off to another player who catches it and makes polymer. And the question is, how good is the transfer of the 1-hexene fragment to the titanium and into the polymer? How do you test that? So lots of isotopic labeling, spectroscopy, but the real telling test is we add 1 pentene to this mixture. Remember, the chromium makes 1-hexene. It's enchained into the polymer, and we get a particular kind of branch, a butyl group. We add 1 pentene in competition. It's like an enzymatic experiment. We add 1 molar, 1 pentene, and almost none is incorporated. So this molecule and the transfer is extremely effective, better than most of the college quarterbacks. So, final question. We go back to the issue of the Haber process and all of these heterogeneous catalysts. What would happen if we put one of these molecules on a surface? It turns out to be a very particular kind of sulfated oxide surface. We use XAFs, a technique to look at the groups around the zirconium, and this just shows you single crystal X-ray, and XAFs gives the same answer. I put it on the surface, and it goes crazy. It's more reactive than anything we've ever been able to get our hands on before. And the reason is that the cation is supported on essentially a sea of electron density of this oxide surface. And here's the XAFs data. This is Alessandro Mota sitting right back over there, is one of the people who did the DFT calculations. We can see this very loosely bound and cation, and you might wonder, well, so to finish the lecture, what is it good for? Here's what it looks like. Here it is. It's essentially the substrate is docked between the zirconium and the anion. So this is a benzene complex. It hydrogenates benzene. And you sort of say, wait a minute, that's a D014 electron cation. They don't do that. They do that. But the interesting thing in terms of what's it good for is when we feed this catalyst mixtures of benzene and toluene, benzene and ethylbenzene, all these other aromatics, which in fact is what is in the gas tank of your car. Your car has about 1/3 aromatics as the fuel. And benzene now is a recognized carcinogen. That has to come out. We need the rest of the aromatics for octane, for performance, for energy efficiency. How do you get the benzene out? It turns out to be a non-trivial problem. This catalyst has a very high selectivity because of the constraining groups around the active center, has a very high selectivity for hydrogenating benzene. So it's a model for detoxifying gasoline. We think it's got a lot of prospects. Okay, so, and this just only tells you that, in fact, the hydrogens, if you look at this little abiotic enzyme, all the hydrogens are added to one face of the benzene ring, and that has interesting applications in terms of catalysis. No time to talk about that. But some acknowledgments. First of all, since the Berkeley people always show the Pacific Ocean next to their campus, I'm going to show you Lake Michigan and the city of Chicago next to ours. And Lake Michigan is about 100 miles across. This is over about the last decade of students who have worked on this project, including Massimiliano Del Ferro, Alessandro Mota, Ignazio Fragola, Alceo Maccioni, Cristiano Sucaccia. So this has been a very international collaboration, and it's continuing. So with that, let me wrap this up and again say how honored I am to be elected to this academy and to meet all of my fellow academicians. So thank you very much.